Up until now, we have only considered charge distributions that involved point charges. We'll now move to an example in which the charge distribution is continuous. In particular, we will calculate the electric field produced by an infinite line of charge. A two-dimensional side view of this line of charge is shown. The big idea here is exactly the same as for discrete charge distributions. We calculate the field produced by individual charges and then take the vector sum of these fields. The only thing that changes is that the sum over a finite number of charges becomes an integral over the continuous charge distribution. We'll now calculate the electric field at the point P on the y-axis directly above the line of charge. Before we actually do the calculation, let's first look at the contribution each segment of the line makes to the electric field at point P. As we move from minus infinity to plus infinity, we see the contribution from each segment of charge, the red rectangle, to the electric field at P displayed as the red vector. The x and y components of this contribution are displayed as the blue and green vectors. Note that as we integrate from minus infinity to 0, the x component of the E field at P, the blue vector, points to the right. But once we pass 0 and move towards plus infinity, the x component of the E field at P points to the left. Here we see a plot of dE sub x, the x component of the E field at P produced by an element of charge dq located at position x. The value of E sub x, the x component of the total E field at P, is equal to the integral of dE sub x over x, which is represented as the area under the dE sub x curve. It certainly looks like this area is 0, and in fact, it is. We can understand why E sub x is 0 by considering the contributions to the integral from two segments on the line that are equidistant from P as shown. The magnitudes of the E fields produced by these segments are equal since they are the same distance from P. The directions of the E fields produced by these segments, however, are not the same. In particular, we see that the x components of the E fields from the two segments exactly cancel each other. Since the line is infinite, for any segment we choose at minus x, there's another segment at plus x that will produce an E field at P whose x component exactly cancels the x component of the E field at P produced by the segment at minus x. We will now focus on the y component of the E field at P as we integrate from minus infinity to plus infinity. We see that all segments of the line now produce E fields at P with positive y components. The plot of dE sub y as a function of x is a sharp peak, centered at x equals 0, as shown. To find the value of E sub y, the y component of the total E field at P, we integrate this curve from minus infinity to plus infinity. This integral is represented by the area under the curve and is a positive number. We'll now move on to compute this integral on the next slide.